Karen. I'm not sure I like the label of the second mic, but I'll live with that one for now. It's fine. I'm happy to defer to the first mic. Yeah, I'm going to talk today for a short time about geotechnical characterization for FEA. A subject, much like ground models, that you could spend hours talking about realistically to do it justice. What I'll touch upon today is essentially some... yeah, okay. There we go. So some observations from essentially my experience of having worked on wind farm projects, oil and gas projects as well, where FEA has been initiated, and hopefully just to provide some thoughts and some topics for discussion, essentially to provoke a bit of discussion and engagement in the subject. So essentially the benefits of FEA-based design are well understood at this stage. There's a lot of recent publication on the use of FEA for various foundation types for renewables or wind turbine structures, just showing the benefits of using FEA essentially as a means to allow us to more accurately replicate the physics of the foundation design problem, which can lead to gains in terms of foundation sizing. But it should also be mentioned that actually FEA is also a tool that we can use to manage foundation risk. So as well as making sure that we get the most out of our soils data and capturing soil response to our benefit in terms of reducing foundation size, FEA also allows us to implement that more representative soil response to capture any risk that may pose. So some soils may respond in a way which is for which current design methods provide a cautious representation, but there are also soils which respond in a way for which current design methods may provide a non-cautious representation. Perhaps that's where the focus needs to be. I think acknowledging the fact that we're looking at risk as well as reward from these analyses is particularly important. Essentially, in terms of the renewables sector, we think about design for wind turbine foundations, we think about monopiles, we think about suction buckets, and to potentially a lesser extent in terms of use of FEA, we think about jacket piles. Now for monopiles, FEA has been much discussed recently via the outcomes of the PISA joint industry project, which obviously highlighted the benefits of using an FEA-based response. And in fact, to such an extent that really, for monopile design and for suction bucket design, the simplified conventional offshore rule-based assessments contained in sort of ISO and API code are really not doing the job to adequately constrain that design case. And therefore, FEA really is a key to moving the design process forward for those foundation types. But ultimately, since we're used as offshore engineers to parameterizing and to characterizing our soil to feed into code-based design assessments, is really our approach to geotechnical characterization now actively addressing the requirements of FEA, which are significantly more demanding than our previous design assessments. So just to illustrate that, it's useful to go through the conventional design assessment and just see how the parameterization affects that. So here we have the lateral response of a pile in accordance with the API type model. Here we have a 1D model to which we connect springs, which represent essentially the interaction between the pile and the soil as we provide a lateral load or introduce a lateral load to that pile. Now previously, when we were doing characterization, what we're looking to generate is a profile of parameters. In this example, we're looking at a clay soil, and we're generating a profile of undrained shear strength with depth, and we're highlighting the variations in that profile as we go. And those spot measurements, so single figure measurements of undrained shear strength, are used to infer a design profile from which we generate empirical curves in accordance with the API code-based relationships. For some reason, we also develop cyclic curves for that, and often there's even no cyclic data on which we base those. But conventionally, we might accept that this is generally, for most soil types that we find in the North Sea, certainly a conservative representation of the actual response. However, it's not often, in my experience, or perhaps in many of yours, that we go back to the actual lab data and we say, well, we've actually measured the stress strain response of this soil in the lab. how does that actually represent what we're putting together now as our design representation of the way that soil will interact with the pile and the lateral loading? That's where things differ when we come to look at a finite element representation of the problem. Now we've replaced our 1D model with a 3D model, which has very significantly more elements of soil. So thousands of elements of soil in that model. And in the case of the PISA reaction curves, we're looking to define many more degrees of freedom to that model in terms of the curves that are input. So we've got our PY curve response. We're also looking at our moment or distributed moment response and what happens at the base of the pile. So a lot more aspects to this design approach, and Harvey later will tell you a lot more detail about that approach, which hopefully then makes sense with what I'm telling you here. But essentially, every single element in this mesh or this representation of our foundation needs a response model. So much like we've attached a spring to our 1D curve model in our API method, now we need to attach a response to each of these elements, and all these elements will interact with each other. So essentially, that's where what we term constitutive soil model comes in. This is really just a mathematical representation of the soil response that's used to essentially calibrate or to predict the way the soil will behave under the loadings imposed in the FEA environment. And essentially, the constitutive model response controls the response of the FEA prediction. So while the boundary value and how you model the pile and how you model the boundaries of the problem are also important and highly important in some cases for the model, really if you get the soil response wrong, no matter what you've done with the rest of the boundary conditions, ultimately your prediction will be limited by the errors that you've introduced into the soil response characterization. So characterization requirements, just to take that a step further. The table at the top here is outlining the requirements in terms of the parameters that are input into our code-based API method for clay soils. So we might have in situ some cone penetration test data, in the laboratory some density determinations with the soil, and some basic measurements of strength of that soil. And then we essentially need 3 parameters to generate our curves in accordance with that model. If we look at our FEA-based representation, you can see the requirements become significantly more detailed. Perhaps you need additional in situ data in terms of seismic CPT or pressure meter data to adequately characterize the stiffness of the soil. You're generating a requirement for significantly larger volumes of laboratory data. And if we look at some conventional numbers of parameters to input to the models that we're using in these types of analysis or might be using in these types of analysis, then these values are significantly higher than the 3 single parameters that we're looking at previously for the API representation. And to come into the ground model approach that Mike's taken you through, essentially what we're using is to use our ground model as a predictive tool. And I think as an industry, offshore, we're very good at doing this, which is essentially taking our ground model and extracting those profiles of design parameters with depth. But what we need to be doing as an industry when we start looking at FEA-based design is taking our ground model and finding a way to extract our stress strain response. Because this is really the response which is going to govern what happens in our FEA, and it's going to essentially dominate the prediction that we make using that tool. So we need to start looking at stress strain response as an outcome of a ground model in terms of monotonic response, but also in terms of cyclic response, because cyclic loading plays a large part in the design methodology for offshore structures. Now we bring in the fact, on top of everything else, that the soil response is highly complex. So it varies to a number of different factors or different variables that can be introduced. Essentially, the stress strain response that you measure will vary depending on soil state, whether it's the in situ state or some induced stress state due to foundation loading. Will vary by drainage conditions. You can get significantly different response measured between a drained response of the sand and an undrained response of the sand, for example. And those differences can be quite some severe degree. Soil is anisotropic, both induced anisotropy from changes in stress, but also inherent anisotropy from changes in fabric of the soil itself. On top of everything else, we have to deal with quantifying disturbance in soil which occurs due to the sampling process and perhaps due to reconstitution of soil within the laboratory. So we're up against it from the start in terms of trying to characterise our soil response and capture all the different salient features which may exist. Aside from that, we then need to take that soil response and decide how we're going to model it. So which model are we going to use to represent that soil response in our finite element analysis? Essentially, just a quick Google search on constitutive soil models will bring up in the order of 270,000 hits on Google, which just shows the body of literature which exists into generating, developing, calibrating soil models to represent soil response. And that tells you a lot, really, about the complexities of soil response in themselves, that so much work is devoted to this subject. And I'm sure in the crowd here today, we could name quite a few models. Anyone want to throw one out there, a constitutive model? Let's go and get us started. Fence one, yeah. Okay. Anyone, a more well-known constitutive model? No, well, there's loads. If you take my word for it, Google constitutive models, you'll have many happy weeks reading all the different models that are available to represent your soil response. But essentially what we're looking for in our FEA is to try and balance the complexity of those models. So they exist in different degrees. Because soil response is complex, the complexity of the models varies quite significantly. We have very simplistic models which offer high speed in terms of the speed of the prediction or the speed of the analysis that you run. And we have very complex, what's often termed philosopher models, which have a very high predictive capability, so are able to represent soil response in a very detailed way, but suffer from problems regarding speed and robustness of numerical analysis. So it's up to us really to make a choice in terms of the soil response that we measure for our site and the way we're going to then go about modelling that in our finite element analysis. Typically we might be looking within a range for practical design in what's termed here engineer models, which offer a good balance between speed and predictive capability. But in order to select those types of models, we really need to zone in on the features of soil response which are having the most impact on our foundation analysis. So essentially, how are we doing that? So before we investigate the soil units, we need to consider how we're going to model them later down the line. So really, the key take-home from the talk today that I give you will be the earlier in the design life cycle you consider how you're going to model the soil response, the more productive the outcomes of your geotechnical design or FEE-based geotechnical design are going to be. Because ultimately, what you want to do is have an idea of your soil response model ahead of going out and collecting all your site characterization data, because then you can provide enough data to adequately characterize your model. Otherwise, you end up in a situation where you hand over a soil data set to a designer and ask them to run very complex finite element analysis, but actually you haven't given them any of the data they need to parameterize the model. And then you end up in a situation where that designer needs to make significant assumptions regarding the parameters and assumptions regarding the soil response model, and that ultimately will be handled with conservatism in the design, but potentially those assumptions could be non-conservative if the right response measurements aren't made. So the earlier that we can get those response measurements or an idea of how we're going to model soils into our overall project life cycle, the better the outcomes will be for foundation design. So how do we go about generating the right data set to adequately parameterize a constitutive model? Now, laboratory testing offers a way for us to measure soil stress-strain response in the laboratory, which is often not possible to do in situ. There are certain in situ measurements that you can make, which will characterize the extent of soil response, so at the very small strain stiffness end of the response, or at the very large strain, essentially failure state of the soil. But tracking the generation or the stress-strain response between those points is tricky to do via an in situ test. Perhaps a pressure meter gets you the closest to that approximation. But otherwise, we need to generate significant laboratory testing data sets in order to characterize that stress-strain response. But again, the laboratory testing needs to be scheduled with the model in mind, because different models have different input requirements. So we talk about laboratory testing, which is performed on samples that we take from boreholes at a single location across the site. Now, how do we then convert that characterization of stress-strain response into a site-wide characterization model? And because, as Mike's already said, these offshore wind farm sites cover very large areas with high degrees of variability across the site, And we need essentially a model that's going to be able to, or an approach that will capture that variability and allow for that site-wide design to take place. So essentially what we need is an FEA ground model approach, where we're using our ground model to generate the variability across the site, but we've adequately parameterized the soil units within our ground model to be able to feed our finite element analysis. And essentially, to make sure that that process is consistent, we can link the measurements that we make in the laboratory of stress strain response to in situ test measurements that are available, often from CPT, for example, or potentially from pressure meter data. So an example here, here we have soil units as determined from a ground model or determined during geotechnical borehole evaluation, and we've calibrated a model response to those soil units based on laboratory testing that's done on that borehole location. That location is taken from one interval point across our offshore wind farm site, but now we need a parameterization which adequately and consistently covers the soil response at another location of the site where the same ground units are present. So the same soil conditions, but a different location across the site where elevations of the units have changed. How do we get to a position where we can go from the measurements that we take here at one location to a model parameterization at another one? Do we recalibrate? So do we do position-specific design? Do we take a borehole at every location and test the soils at that borehole so that we can essentially calibrate our constitutive model to every single position? Well, no. Realistically, it's not going to be possible to do that, both in the planning and the budgets associated with the site investigation strategy. So are we better off normalizing that response and trying to predict it on a site-wide basis using our ground model as the chassis for that prediction? Just an example here, not wishing to overcomplicate the issue, I won't dwell on every stage of this, but this is an example of a process map that can be put together to focus on two things. Essentially, our model parameterization are linked to some normalized unit measure, i.e. soil state or some other measure which can be easily determined by correlation to our CPT data. All of our finite element or stress strain predictions for our soil response are then linked to that state measure in some relationship, and that state measure is then predicted at other locations via the CPT, and we check our unit calibrations. So essentially, what we're doing is using the in situ data that we have at every location, coupled with the laboratory measurements of stress strain response, to calibrate a soil model, which can then be extrapolated across an entire site. And once you have that soil model in place, it's then as simple as taking your in situ data, essentially plotting it, and essentially assigning the correlated values of your constitutive soil model parameters from the CPT data. So it's a very powerful tool to use for characterizing at different locations across the site. Here's an example of how, or an illustrative example of how this works in practice, taking response of sand from an example North Sea site, which had highly variable fines content. What we see here is that for one measure of soil response, and in this case it's a drained response measure for that sand, we're plotting the data in terms of relative density, which is a common characterization parameter to use for sands. However, we can see that actually this doesn't give a very good predictive model of our change in soil parameter with our increase in relative density. There's a high degree of scatter for this particular site. When we pick a different normalized state measure, in this case we use a normalized cone resistance value, we see we get a much better prediction of response. And so we select a normalized cone resistance parameter to calibrate our soil model, or essentially as a profiling parameter for our soil model calibration. What we can then do is identify some important features of soil response that we want to replicate in our model. In this sense, we've got an idealized drained response curve, so this is a measure of our stress strain response of the soil, and we have the idealized volumetric change. So as we compress our soil, we get a change in the stress strain response, and also the volume of that sand sample changes. Now, there's three distinct points that have been picked out of that response for calibration. Here we have an initial contraction point in the soil response, then we have a final volumetric point in the soil response, and we have a shear strain at which the phase transformation occurs. So the response transitions from contraction to dilation, so that the sample goes from essentially contracting or compressing under the load to expanding under that load condition. So these three measures of soil response, we then take our laboratory data set and we extrapolate them to our normalized cone resistance. So here we have our laboratory data as the black circles, and the grey line there is our calibration line. So essentially this is representing how we've calibrated our soil model to predict that element of soil behaviour. We take those three different measures of soil response and we calibrate our model iteratively to predict across a site-wide data set with a reasonable degree of accuracy those response conditions. That allows us then for any location where we have CPT data to predict any one of these response measures or the response of our soil or to parameterize the model for that particular location and for that particular soil unit. So some cautionary notes on use of FEA, by no means extensive, but just some examples from my experience. It's critical that when you embark upon FEA-based analysis that you understand the constitutive soil model that you selected to represent your soil response and how that soil model behaves in the boundary value problem. Ultimately, that will constrain or dominate the prediction that you make, so understanding that is critical to really understanding how your results should be applied in design. An important one, again, that we've gone through, pick a constitutive model that's suitable to the data set that you have available. That's made a lot easier if you do your constitutive model selections or refinement at an early project stage. And if that model lends itself to a site-wide normalized prediction tool, then that will be a powerful design tool as long as you can prove some level of caution or conservatism in that response case. And that leads me on to my sort of final cautionary note that essentially the use of FEA-based design, although we know and it's been well publicised it can give us gains in terms of reduced foundation sizing, it's not or should not be a licence to assume better than cautious design parameters. Just because you're using a model which gives a better representation of the physics of the foundation problem, it doesn't mean that you have to throw all caution or conservatism out of the design process. In fact, arguably, it's even more important to understand the level of conservatism in your constitutive model parameterization, because that can be quite a complex thing to try and unpick to define a factor of safety on a foundation. Essentially, it all boils down to a final message that ultimately, if you're not understanding these limitations to use of FEA or to understanding the constitutive model implementation, then really you should question whether you should be using FEA for that particular design condition. So ultimately, we're trying to reduce empiricism in design, but if we don't generate the right data sets from our site investigation, if we don't understand how we're going to be modelling that data down the line, then empiricism will start creeping back into that design process. That's what I've got.